Teams from all around the world come to Battle Mountain in Nevada to race their human-powered vehicles. There's anything from trikes to two-wheelers. The world record currently stands at 144 kilometers per hour. Our ultimate goal is to break that world record.
We're a team based of around 50 members, split into 5 sub-teams, and our 2 sub-teams that use Ansys the most are the chassis team and the aerodynamics team. Our human-powered vehicle takes the form of a recumbent bike, and our rider lies within this bike and is encased in an outer shell that improves aerodynamics called a fairing.
Our current goals within the aerodynamics team are to design a new fairing with 50% less drag than our current fairing. At the moment, we've reduced the aerodynamic drag by about 30% using Ansys. However, we're confident that we can reduce it further to meet our goals. So because the fairing is an opaque composite, the rider actually can't see out of the fairing. So in order to allow the rider to see where he or she is going, we use a camera mount which sits above the rider's head external to the fairing. So this is the old camera mount which contributed to roughly 20% of the overall drag on the fairing. So we decided to create a new camera mount with less aerodynamic drag. After creating a number of different designs and testing using Ansys, this was the optimal design that we came up with, which contributes to only around 5% of the overall drag on the fairing.
Because we're a student team, we're quite limited in budget, and a human-powered vehicle is a very costly project to get done. Because of this, we use Ansys quite early in the design stage to test our various designs. Safety is of paramount importance for our team, especially for the chassis sub-team. Our previous bike was quite flexible, and this resulted in less stability, which was of course quite risky for our rider. With our new bike, we had a higher speed goal, and because of that, we needed a safer bike. We've used Ansys from the very early days of our team, from version 1 to the improved version 1.5, and to our latest bike, Wombat, where we achieved our highest personal speed ever of 78 kilometers per hour. One of the main changes from version 1.5 to version 2 was the shift from solid steel panels in our chassis to a tubular space frame design. This change allowed us to improve deflection quite significantly, especially near the crank of the bike, approximately by 70%. When we begin the design process for a new chassis, we're often reliant on the fairing provided to us by the aerodynamics sub-team. With the use of Ansys, using their fairing concepts, we can begin the design of the chassis as fast as possible.
So post-processing with Ansys gives us a very visual picture of what's happening around our fairing and helps us to really understand what's going on and make design changes accordingly. In the early stages of our design, we tested 10 tails, which wouldn't have been possible to test them physically in the wind tunnel. Due to manufacturing constraints, we weren't able to manufacture this tail to a fine tip. So with the advent of 3D printing and by using Ansys simulations, we were able to create this retrofitted tail, which reduces the overall drag on the fairing by about 10%.
A future project for the chassis team is the new composite-based seat. We're planning to use composite FEA to design this seat. The Ansys Composite Prep Post tool allows us to simulate factors such as draping and different layers, as well as how fabrics interact with each other, making the design process much more streamlined.
Our next design phase will use Adjoint Solver to refine our model further and push the boundaries of what we can achieve.
As a mechanical engineer, Ansys is an essential tool. It allows me to simulate complex load cases and test minute variations in design much faster than if the software didn't exist and I had to do everything by hand. Because of this, I want to keep improving my Ansys skills in the future and utilize the technology to its maximum potential.